Hi, I'm Greg Cohen. I'm a scientist at the National Institutes of Health, and I'm very happy and proud to introduce our next speaker, Dr. Brad Sutton, who is at the University of Illinois in Champaign-Urbana. Dr. Sutton received his degrees in general engineering from the University of Illinois, and then went to Michigan for a couple of master's degrees in biomedical and electrical engineering, then got his PhD in biomedical engineering from Michigan. It's a Big Ten kind of thing. He's been at the University of Illinois since 2006. He is a professor of biomedical engineering, and his research program is in interest in developing magnetic resonance imaging acquisition, image reconstruction, and systems modeling approaches to understand brain function. Today, he's going to be telling us about leveraging correlations in dynamic MRI data to enable high-speed imaging. Brad, thank you for joining us.
All right, thanks for that introduction. And yes, what a great transition at the end of Kazu's talk to tell us what we're going to talk about in this one, which is really, we can't get enough data and we need some modeling in order to be able to compensate for the lack of sampling. And so hopefully you'll understand that. I want to go through and first of all tell you very excited to be giving this talk and learn more about the overlaps between these disciplines, and have been using gridding and non-uniform Fourier transforms for a long time and been benefiting from a lot of the work that was done many years ago. We also have lots of other interesting intersections outside of image reconstruction and sampling, and one of them I wanted to bring up is from one of our founders, and that is, here is the list of Nobel Prizes in magnetic resonance imaging leading up to where we are today. And you can see a lot of people over many years developing quite a few technologies to get there, but we're going to focus in on this 1952 block here. And in 1946, Felix Bloch and Edward Purcell discovered the MRI phenomena in condensed matter, and they got the Nobel Prize for that in 52. So what do you do when you develop something big and then you're waiting for your Nobel Prize in 52? Well, Edward Purcell was the first to detect galactic hydrogen emissions at the 20 centimeter wavelength with radio spectroscopy. So, and that was published in 51, so in the middle. And we had another good example with Neb Durek to start off this seminar series too, of people realizing the overlap and aiming their antenna to outer space instead of to the brain. All right, so I'm going to give you a quick overview of MRI physics and sampling so that we can get to the same equations that we were seeing in Kazu's talk, and then we'll motivate our need for speed. We can't sample enough, fast enough. Things are moving. We're not in control of that, and we really need to get our data in a reasonable time. And we'll talk about some models that will do more than just regularize, but they will drastically reduce the sampling requirements to be able to give us faster imaging. And I'll give you a toy example and some code that you can try out yourself, and then I'll show you an example of how we've applied that to speech imaging. So I'm going to build off of the wonderful foundation that Dan Sodikson laid last time, and he set the bar quite high. So I'm simply going to steal a few of those and hopefully leverage that to move on. And as he said, MRI is a story of three magnetic fields. So we have the large B0 field, which sets the Larmor frequency at which the protons are resonating, and that's the signal we're going to pick up. And then we have an RF field where we can excite those protons and we can detect their signals through our RF coils. And then we're going to have gradient magnetic fields that change the magnetic field in different directions to be able to let us localize where those protons are coming from. And this is a slide from Dan just to show we can put a magnetic field across the sample and we can get very different frequencies coming out of one side of our sample versus the other. And so at a weaker magnetic field, we get a lower frequency, higher magnetic field, higher frequency. And he showed projections. I'm going to build this up into our case base so we can talk about why in MRI it takes us so long to sample and why we're trying to get away with fewer samples. So basically what I'm going to show you is we have our main magnetic field and we have our protons that have a magnetic moment, and we've excited them so they're in a perpendicular plane and they're going to precess, and they're going to precess with a particular frequency related to the magnetic field, and then also any gradients times their position. So as we showed, they spin at a higher position. And so the main magnetic field in green here and our protons in red, they're spinning around, and what we do is we put a coil next to this and we can pick up the EMF We can pick up the magnetic field variations from those spinning protons, and that's what produces our signal. We induce currents in our coil. So the cumulative angle of those protons spinning around is really, how much they've spun in a certain amount of time. So they're spinning at a certain frequency related to our main magnetic field, but then they're also spinning at a frequency related to the gradients that we're applying. And so we can make those gradients have different waveforms. They don't just have to be turned on and off. They can have very different waveforms. And so if we integrate up all the gradients up to a certain point, that tells us how much the cumulative angle has occurred, and that's going to give us our K-space, okay? And so the K-space is the same K-space that we have in radio astronomy. We need to sample that K-space, but this is how we get there with MRI, is we play out these time-varying gradient waveforms, and we integrate them up to see where we're at in K-space. So when we acquire our data, we're not really worried about this really high-frequency component around the main magnetic fields, which for a 3 Tesla scanner is 128 megahertz. So we can completely get rid of that part, demodulate it out. What we're interested in is all the other variations in phase and frequency related to how the spins were reacting to the magnetic gradients that we applied, because that's going to tell us their position. So if we get rid of that B0 component, the main magnetic field, we end up with a signal equation that looks like this, where we simply integrate over our whole sample. We're going to have our image I. I tried to make our notation similar. And then to Urvashi's last month. So we get our image that we're going to try to reconstruct, and we have the Fourier kernel here, and that's going to give us our signal in K-space. So it takes time to journey through K-space though, because we really have to accumulate this phase due to these gradients being applied, and we're limited on how fast we can turn those gradients on and off. And some of that limitation is due to power, but a lot of it is due to physiological constraints. If I switch gradient fields too quickly, we induce currents in your nerves and can cause some physiological effects. So if I want to go through K-space in a spiral pattern, I want to sample everything in a spiral pattern, I would play these growing sinusoidal waveforms. So for example, the red one might be the KX in this direction, and the blue one will be the KY, or be the Y gradient in this direction. And if you integrate these, you start to play out, you start to sample this trajectory as you go through. And it takes time to move through. I can only have so much amplitude, and I can only change my gradients so quickly. And so it takes time for us to fully sample that K-space. I have a couple of examples of some of the more traditional waveforms that we use. And I hope that this will bring back memories of Urvashi's did a very similar movie to this last month. So hopefully this will look familiar. But what I'm going to show you here is for echoplanar imaging, which is we're going to sample K-space. This is our K-space here. We're going to sample it in a regular grid. And at each point, you can see we're down here in the corner right now. We're going to show you the real part of the encoding, because we're just sampling in Fourier space. So we're going to get these Fourier encoding functions at each position, where we are multiplying every point in our image by this encoding function and summing them all up. And that's giving us our signal at that location. And you'll be able to see the gradient waveforms required to move back and forth in order to get there. We like this trajectory because at the end, we have a Cartesian sampled K-space, and we can simply take an inverse Fourier transform in order to reconstruct the image. And so you can see the blue is the X gradient. We're going back and forth across K-space. And then in between, we're just blipping up a little bit, and we're accumulating just a little bit in the Y direction as we go through this space. And so this is one way to acquire. We may want a more efficient trajectory. And so this is a spiral acquisition, which is very similar to those waveforms I just showed you. And you can see we start at DC now in the center K-space, and then as we move out, we increase the frequencies as we go around. So why might we want to use spiral sampling? Well, after some initial time to ramp up the waveform, it's going to hit a maximum amplitude, and it leverages your gradient performance very efficiently. You can run at maximum gradient. You're simply mixing between the X and the Y direction as you go through, so you can get some nice efficiency to your acquisition. But there are physiological stimulation constraints here where we're constantly changing directions, and those can induce a stimulation. Whereas with the EPI sequence, we get to the end of a line, we have to turn around and come back. And then the reconstruction is a little more challenging here because we end up sampling on the spiral trajectory. And so we have to do some extra things for reconstruction. But life is more than 2D, okay? So we have dynamics, we have other things that we want to see. We may have spectroscopy, as we mentioned. We may have polarity, we may have other components that we want to pull out of data. So just sampling K-space is not enough. Radio astronomy is very multidimensional, and so just another slide taken from Urvashi from last time, just looking at some of the other dimensions that might show up in radio astronomy. And you can end up with 4D and 5D, and we need to sample those. And one way you could do it is you could try to sample in a snapshot type mode, where you take one image at each location in the dimension you're trying to sample and try to put those back together. But it turns out that's going to usually take way too long to sample those, and you're going to end up with a lot of artifacts at the very least, or you're going to end up with a really long imaging time at the worst. MRI is also more than two-dimensional. We have very high dimensional data. I show some examples here just to give you an idea. So the basic is the object you're imaging could be moving, and we're going to show this example later on in the talk, which is somebody speaking while the MRI scanner is running. We could have different contrasts that we're getting during the course of the acquisition. So this is the same brain, but it has different diffusion weighting, and you can see white matter and gray matter showing up differently in the brain, and different structures showing up as we weight those differently as we acquire the data. And also for every chunk of brain tissue in each one of those pixels in our image, they have lots of different things in them. And so we have spectroscopy happening with MRI, where we might want to decompose the signals from different molecules in the brain. And those molecules all have protons that have very different local environments to them, and they give us different frequencies, slightly different frequencies out. And we can encode in that dimension, and we can try to separate out different metabolites in the brain, like NAA, which is an indicator of brain health. So we have a very multi-dimensional data set, and we have to sample all these dimensions. And like I said, if we have to sample with the snapshot imaging approach, it's not going to work. And so we aren't going to be able to sample fast enough. Before we address that sampling issue, I just want to pull together the signal model for MRI. We've talked about K-space trajectory and how we sample, and we talked about how the signal is basically then the Fourier transform, okay, with that K-space trajectory. And I tried to color code these things so you can see what we're talking about. This may be the image we're trying to get. And there's a couple of other effects that may happen too. And just listening to Kazu's talk, there's a lot of things that can happen to blur the image. And so we have magnetic field and homogeneity. We expect the magnetic field to be uniform, but there are things in there, including air spaces in the brain that disrupts the magnetic field uniformity, and those will cause blurring. We also have several different antenna receiving in our receiver coil, and those weight the image differently. They're most sensitive to the parts of the brain that are closest to them. And then we may have model functions for the voxels too. So we have this equation here, and what we're typically going to do is an inverse problem approach. So this is my K-space data samples, and I actually measure noisy versions of those, so we can put the eta n in here, and I think that was the same one we saw in Kazu's talk. And then we have an image model associated with our noisy data samples here, and we can form that into a matrix vector expression. And then what we're going to do is usually an inverse problem approach here to get back. So we can do some type of least squares approach for image reconstruction, where we take our noisy data, we take our current estimate of the image, and we have our physics in this A matrix here, and we try to simulate what that data might look like and compare and update. And then we can add regularization. And Kazu mentioned a couple of regularizations. We use a lot of the same regularizations too. And so it was nice to see those in there too, and Tikhonov and other things showing up. But usually the problem is ill-conditioned, and we need to use regularization. Usually we didn't sample quite enough either. And so we need to be able to enforce that, be able to get better estimates of our image. In MRI, I will point out that we are in the complex Gaussian noise domain, which makes some of this a little bit more straightforward too. All right, and for us, we're really focused on calculating the forward problem quickly, and we need the forward problem and the adjoint, and so that for the inverse problem approach, that's what we need to calculate. But we end up with this issue with the sampling that we talked about just a minute ago, which is if I have four-dimensional data, which is what I'm showing here, I have a 3D image, and I have time, and I need to make lots of samples. It's not going to work to do snapshot imaging, where for each plane, let's say each plane across this oral cavity for speech, I take the time to take an image and fully encode K-space, and then I go to the next one, and I go to the next one. It's not going to work out. And with regularization approaches, we can start to leverage some shared information across those different slices. but still, we're not going to end up with enough sampling to be able to make this image. So I'm going to give you a motivating example from this data set, which is the matrix size here is 128 by 128 by 32. I think it'd be interesting to talk about matrix size differences with our two domains. I think MRI is getting up to 1,000 in one dimension, but that's about as big as we go right now. But 132 by 132, or 128 by 128 by 32 pixels at 40 frames per second. And if you look at that, that means I need to sample over 21 million complex valued samples per second in order to Fourier encode at this frame rate. And that's assuming I can even get to those case-based locations. It turns out my gradients will not allow me to move that quickly, and there's physiological stimulation limits. And then in addition, I'm not just sampling the whole time. I have to excite the spins. I have to spoil the signal from the previous set of spins that I excited. And so I can't use the entire time in order to get that data too. So there's no way to sample this with the snapshot approach. We need a different way. And so for this, we end up having to look at how we're modeling the image itself, the four-dimensional image itself. And we need to look for images in a domain that captures what we're looking for, but limits the amount of independent pieces of information that we have to estimate from our data set. And we need to start thinking of this as a 4D estimation problem. So our strategy is going to be to look at different data models for the actual functions we're trying to image. And so instead of just looking for L2 functions or band limited functions even, which would determine what Nyquist rate you need to sample in time for the dynamic aspect of it, we need to limit it further. And so you could say sparse functions too. We need to look for functions that are sparse. That will help some, and you can get by with sub-Nyquist sampling then. We're going to tell you about partially separable functions, and those really allow sub-Nyquist sampling, and they allow me to take reduction factors of 1,000 or more per image and still produce really good images of those dynamics. So what is partial separability functions? Well, the partial separability model is basically looking at the, in this case, this is a three-dimensional image here. It's 2D by time, and realizing that each pixel does not have an independent signal. So when we do Fourier sampling, we're assuming that every location in the image is independent. But when you look at real images, you find that there are a lot of spatiotemporal correlations. And so instead of imaging each independent pixel at each independent time point, what we're going to do is make an nth order partially separable model where we can represent our entire four-dimensional data set by a sum of just a few spatial maps and then temporal functions. Okay, so this is a 3D spatial map and a 1D temporal function to get back to our 4D space. So what is a separable signal? Well, there's strict separability. So this is a four-dimensional signal. I could separate it up into 4 different functions, okay? And you can imagine if I had a box that was moving, I could have a rect function, and maybe another rect function here, and then some time function with how the intensity was going up and down. That would be strictly separable. Most of the functions we're going to see are not, but instead we're going to do this nth order partially separable, that we're going to have a three-dimensional object, and it's going to have a time variation. And when we add these back together, we get a good representation of our original 4D data. And L is going to be the rank of our low rank approximation for this. So what type of signals are separable and low rank? So if we start looking at this to kind of understand what is there, we might look at this, and this is a cardiac waveform. This has got an arrhythmia, which means there's an irregularity in the heartbeat, and this is corresponding with respiration. But this is definitely a partially separable signal. So there's a lot happening here. There's a lot of structure, but this is very well captured in a very low model order situation. Here's another example, the spectroscopy imaging I was talking about before, where we're trying to, for each pixel, look at the chemical information in that pixel. And we need to take a really long readout to look at all these very closely spaced frequencies along that dimension. Well, this is also a low rank signal. The underlying structure of the brain is very much shared between them. And we have just a few components, a few different chemicals in there. And so it's really easy to understand that this is just a mixture of several functions there. All right, so how do we do this? This is our low rank model here. So we're gonna take our 4-dimensional K-space, break it up into 3-dimensional K-space maps, and then so those are called, I forgot the word, visual So, but we got our 3D K-space maps and then our temporal bases here, and we're just going to have L of those as we go through. What we would really like to have is a full data matrix, okay? This data matrix has signal along the three-dimensional K-space on this axis, so fully sampled 3D K-space on this axis, and then this axis is time for that fourth dimension. And this is our full data matrix. This is called a Casarati matrix. We like to have this completely sampled in order to be able to get our image, but it turns out we're not going to. We're only going to have very few of these points sampled. And our goal is to take this undersampled matrix and figure out what the actual full data matrix is in order to be able to recover this. But we know that the rank of that full data matrix is something low. It's a rank L. So what we do in our MRI data is we mix it up a little bit more, is we can separate out the temporal information from the imaging data. So what we're going to do is going to have two simultaneous data streams where we get to decide how to sample each of these data streams independently. And we're going to get a navigator data where we sample the same space locations every single time point over and over again. We don't have to make an image from them. I show them all in the center of this data matrix here. They don't have to be in the center. We're going to use a cone, a twisted spiral. But we're going to sample that same location every time, and that's going to give us all our information about how things are changing over time. And then we just grab a couple of other samples in K-space, and I need to, over the course of my whole data acquisition, try to sample all of K-space several times over in order to be able to get these spatial maps at the end. So this is our sampling, our navigator data. We're going to do a 3D cone in K-space because it can be done very fast. It's very efficient with the gradients. It gives good coverage of K-space. We sample lots of different spatial frequencies with that acquisition. And then for our imaging data acquired right with that in the same TR, we're going to acquire one line of K-space. Why just one line? Well, it's because it's a really high bandwidth, really easy to reconstruct through just a Fourier transform at the end for the imaging data. It's really easy to deal with these short acquisitions. They have very little artifact left in them. So every time point, we're going to acquire a navigator imaging data and repeat that over. And then at the end, I take all my cones, and I think I flipped the order here. So this is the K-space direction, okay, for the first time point. This is K-space for the second time point of just this cone data. I arrange it like this, and I do a singular value decomposition, and I'm going to take the ELF, just 10 or 20 right singular vectors from this, and these are going to give me my temporal waveforms that I've detected in the data. And then I use those temporal waveforms, and I go back and I estimate the spatial maps from the imaging data, which is really high fidelity imaging data sampled specifically for the purpose of getting really good images. And now I just have to estimate those L spatial maps to go with that. And so I end up with L spatial maps. And when I'm done with that, I take those time series and the spatial maps, and I mix them back together, and I end up with my four-dimensional data set in order to do the dynamics. You can combine these with constraints too. So as we're estimating those spatial maps, you can say, well, my spatial maps are also sparse. And so that will help us get by with even more undersampling. In the case of the four-dimensional imaging, with the 128 by 128 by 32 by 40, for every single frame, we're basically acquiring one line in K-space. So our undersampling factor is 128 times 32. So really high undersampling factor. So you may want some extra regularization in those spatial maps in order to estimate things that match your prior information on what the image properties of the image should be. So I have a toy example, which I'll run through really quickly. And this is available at the GitHub link here, and you can download the code and run it. And everything I'm showing you is directly coming out of the code. It's making the plots and the movies for you. If you have any trouble, just contact me. We're going to have a 64 by 64 matrix size, so a 2D image, but with a third dimension of time. We're going to have 1,280 time points. The navigator is just going to be the center line of K-space. I'm just going to take one line, and the imaging data is just going to be taking another random line in K-space, okay? So I made a simulation object like this. For medical imaging, I'm thinking about the heart and breathing and things like that. This is our K-space sampling. The navigator sampled every time, and I get one random imaging line. But how does this correspond to what you might want? Well, if we look, it's actually not too bad compared to maybe things that you might be looking at yourself. Okay, so and as Kazu talked, there's there's limited time at which these views are available. I think he said 20 minutes, and so so you may need to incorporate some of these approaches. All right, so the first thing you might do is just a sliding window. Just keep your aperture open long enough and average that data together. I can sample all of K-space and I can make an image. If you do that, you're not going to get a very good image. And the reason is things are dynamically changing inside that window, and you're not actually able to capture that relationship. It really is dependent upon which spatial frequencies you sampled during which part of the motion. And so as you can see, we really don't see any of the features of that motion I showed for the true object. Okay, so sliding window is really not going to work for this. So instead, we can take the singular values of the temporal navigator and determine our temporal bases. Here is the ground truth scaled singular values for the whole acquisition. I have the whole images, I have ground truth, so I can look at this and you can see the rank of this is 10 or less. We're capturing most of the image information in a very small number of components. So when you think about having 1,280 images, and really I'm only going to have to estimate 20 spatial maps and get 99% of the information back. Here's what those components look like. We could try to understand something in there. We have two objects moving. We can kind of see some of the periodicity of this, but I've been looking at these maps a lot and trying to understand them, and it decomposes them in the image in a way that doesn't match with what exactly you're looking for. But we're going to keep the first L equals 10 components from the navigator, and we're going to stick those back in. And now we're going to run our least squares estimation to estimate the spatial maps using those temporal navigators, and then our Fourier transforms, coil sensitivities, and everything in here. And we're going to use least squares to solve for this. We need an efficient solver. Here's what the first 4 spatial bases look like. And hopefully these kind of make sense. They each have their own time series. The object is growing and shrinking. And so we have things that look like the spatial derivatives of the object here. Okay, we can put those back together. And what do we get? Well, now just a rank of 10. So instead of estimating 1,280 images, I estimate 10 and I mix those back together. And we can see that this was well represented by the low rank information. And we've recovered the dynamics of this object. And there was no other way to recover those dynamics. We can't sample fast enough to get that information. Okay, so back to our motivating example here. We have this 128 by 128 by 32 matrix size speech imaging that we're doing. The subject is just in the scanner reading a computer screen that has the rainbow passage, and probably people are not familiar with them, but it's the one that sunlight strikes raindrops in the air and turning it into many beautiful colors. And so the person's going to be reading that, and we get near isotropic 2D or 2 millimeter resolution. We get full vocal tract coverage, and we get 40 frames per second, which at the end of a 20 minutes, we have them read the rainbow passage several times. At the end of 20 minutes, we get 48,000 3D volumes to deal with here.
That is not reflection, but reflection by the raindrops which causes the rainbows. Many complicated ideas about a rainbow have been formed. The difference in the rainbow depends considerably upon the size of the drop.
Okay, and we're interested in things like tongue movement and velar movement here to understand. But you know, and when I'm playing this, we're all looking at the center slice here. But it turns out there's significant information in the other directions too. So let me just show you that first. So because we have a full 3D volume, we can of course look and see what's happening with the tongue over time.
That is not reflection.
Okay, we'll stop that. But we can also look across the tongue, and we can actually see the tongue grooving as we say different speech samples. We can watch the tongue groove. And we're actually using this in a study to look at cleft palate individuals and to see how, when surgical repair of different muscles in this region happens, if we restore motions that are more similar to healthy control subjects. And so this really allows us to see 3-dimensionally what's going on here, whereas there's no other way we could have sampled that. Let me just go back to this. So there's really high potential from these low rank models. They can drastically reduce the sampling requirements for dynamic imaging. They enable higher speeds, larger 3D volume coverage. You might get higher spatial resolution. You can spend your time getting exactly the type of imaging information you want, and you can design temporal sampling to match what you want temporally too. It's very useful for signals that are separable and sparse. But the good news is a lot of things are. And so be interesting to see how separable and sparse the information that you're working with in radio astronomy is. The more dimensions you have, the more separable and sparse things become. So reconstruction is computationally demanding. We have a large size of the final 4D image. I said we had 48,000 3D volumes. And we need all the data to make the full dynamic time series. So, and I'll tell you a little bit more about there are some approaches that can help with that. It's a nonlinear reconstruction. Exercise caution, we're throwing away some things, and so you may want to pay attention to what's happening when we pick a model order and we start tossing out some of that information.
That is not.
The computation can also benefit from partial separability. I just want to point out this idea of representing complex functions with a partially separable model, holds in computation too. So we have a discrete forward model for MRI with background field gradients. We end up with a term. Here's our image. Here's our Fourier kernel. But we end up with this term that depends on k-space and the image, which makes us not able to use the fast Fourier transform. And a lot of times we have to go back to a discrete Fourier transform matrix evaluation, which is very slow. But it turns out we can take the problematic term and we can actually represent it by a small set of other operations, so maybe 10 or 20 other operations, where we can then split these up. And by adding all these back together, we approximate the original function. But once I split it up, I can absorb this spatial term into the image, and then I can evaluate this by FFT to get back to k-space, and then simply weight k-space by this, and then sum them up. So this approximation enables us to use 10 or so FFTs to evaluate the kernel instead of having to do discrete Fourier transform over thousands and thousands by thousands of thousands of matrix. All right,
Brad,
so that, yep.
Okay, you're wrapping up. Okay.
Yeah, perfect timing. All right, so so I just wanted to put a couple of acknowledgements here. Kazu gave me a crash course on black hole imaging. I very much appreciate that, and we were very surprised at every turn to see how much overlap there was. I also want to thank Neb for the introduction, and then Dan and Urvashi for setting the bar way too high. So hopefully we have kept your interest up, but certainly I encourage you to go back and watch their talks again if you missed them. And then Jipe and Fan for giving me a lot of material that went into this talk, and Nicole for inviting me to do this. My lab, especially with 2 students that are working on the speech imaging, Riwei and Maojing, and then the Biomedical Imaging Center. I encourage you to go get the code. And then I also encourage you to come visit Illinois sometime soon if you want to learn more about MRI. I show here we have a new MRI museum where a couple of years ago I found Paul Lauterber's first 2 human MRI systems from back in the 70s, and we put them back together and put them on display with his original data the very first time he got MRI to work and things like that. So you can come see how it's all done. And with that, I'll take some questions.
Does not look like there's a question. However, there was a comment that some of your reconstruction methods look like ASP clean. Is that a fair comment?
So maybe Kazu can comment on that, since I don't know what ASP clean is. Yeah.
Well, I think it may be nice to have a comment from Sanjay, actually, who made a comment. I think he should be able to speak.
Yeah, this is Sanjay. That was my comment. ASP clean is, ASP stand for adaptive scale pixel model imaging, where the algorithm that Kazu described as clean does not recognize correlations in the actual image, and ASP clean actually formally recognizes. It looks very, very similar to what you described.
That's great. Yeah,
it is unfortunately not very well known in radio astronomy yet, but it is going to get deployed, and I think more use will happen.
That's great. Yeah, and I think there are quite a few low-rank image reconstruction approaches too, which do start to leverage spatial temporal correlations. I will say that one of the things that we have just found great about this this partially separable model approach, and this explicit formalism that we have, is that we have redesigned the way we acquire temporal information and spatial information separately from each other. So we've redesigned our acquisition has changed completely to accommodate this type of data. So it's a little bit more than just applying, a voxel-based, model that incorporates the spatial temporal correlation after the fact. We're actually specifically acquiring data for our model now, and that's allowed us to go even 10 times faster than we were before.
Thank you.
What's the next technological step that would accelerate your work?
Yeah, I think right now we're still sort of developing these pieces and trying to get the computation to work out to be able to reconstruct these models. I think incorporation of these additional regularization terms into these other advanced models for objects will be very important. And so there are machine learning regularization-based methods that are self-trained or trained on the data itself. I think these things are going to be very powerful to incorporate too. So I think people are going to have to figure out how much prior information can we inject and still preserve exactly the information that we're hoping to get out of our data. What does the error look like? Maybe these Bayesian approaches are going to need to come back into MRI, and we figure out exactly what our uncertainty is associated with the different estimations that we're making.
So this is along the lines of learn regularizers that Dan was talking about last time, right?
Yeah, I think those are just starting to show up, and I think those are going to be really great in terms of trying to learn from it's also changing the way you sample the data, trying to learn from a data set what the underlying object properties are, and then being able to enforce those and train a regularizer that helps you then reconstruct the image.
I saw the first one of these in radio just pop up on the archive a couple of days ago.
I mentioned SVD for compression in the video reconstruction process. Would it make sense to use higher order tensor decomposition, such as tensor train, in case you can achieve higher compression factors? So yes, it turns out if you can use higher order tensor decomposition, you can really reduce even further reduce the amount of information that you need to estimate out of an image. So one thing you might imagine too, like if you looked at the beating hearts, so there is some work in MRI where people have decided that different regions in the image might have different underlying representations, and you can separate out those regions to have different subspaces associated with them then that you can model. Maybe you have fairly static regions in some place, and you can use a really low order tensor to represent that information, and then you have very dynamic regions in other places that you need to spend more of your sampling and more of your modeling on that. But yes, definitely all these things, these are prior information on the model, on the image you're trying to measure itself in, and that really does help reduce the amount of sampling that you need to take to estimate those parameters. There was a couple in a row here that are related to the motion model, whether imaging, instead of imaging, I have just a pixel magnitude sort of model that I'm looking at in my low rank approximation, and Leon Axel asks about whether there is a better way to, if you were to actually model the motion of the object itself. And I think if you incorporate a physics model for the object, and if that's really your goal, is to estimate that physics model, then of course it is going to work much better, and you can incorporate prior information that's more physically accurate, and I think that would be great. I'll tell you one quick thing that we're doing recently associated with this is that I'm going to end up with 48,000 3D volumes, and we're doing this study on kids with cleft palate. Instead of looking at every single motion associated with every single subject, we are building a spatiotemporal atlas so that we can start to look and see how is each individual subject different than the atlas to be able to focus in. And what you can do is you can deform the atlas to each individual subject. It's a spatiotemporal atlas, so you know exactly how the sound ka is going to happen, and you can deform that to that subject, and you can start to represent a lot of the dynamic information just from that warp to the atlas, and you're left with a very small residual problem left to estimate how that individual sample is different. I'm not sure if all black holes share similarity, and there should be an atlas, a spatiotemporal atlas for black holes, to know whether that covers to the other side. But I think it would be interesting incorporating all the information that you have in order to reduce the sampling requirements.
There's another question for you, Dr. Sutton. How critical is the separability of the time, frequency, spatial models in the types of joint reconstruction you described? Is it better to define this based on what is easier to model, or what may not be so low rank but better fits to the data?
Thank you very much for the question. I would say that because we're partially separable and we add components together, we've not seen too many things that don't decompose with a small number of components. Even things that initially look like they might not are very amenable to this. So is it better to define this based on what's easier to model, or what may not be so low rank? Yeah, so I guess the first dimension that we're estimating spatial maps. So I think what your question is getting at is, I do estimate full spatial maps. Spatial maps may not be, they may have a lot of information in them, although I probably am going to assume that they're sparse, and I could take them to a domain that's actually sparse and then reduce the amount of information we have to estimate. I think these are good thoughts. I know I haven't answered your question. I think these are good thoughts. If you can compress the information or make it sparse in some domain, then you probably do help yourself out by limiting the number of coefficients you have to estimate later, and thinking about that in advance. I think it's also important to think about how to sample that information. And when you set up your sampling strategy, that you are sampling in the domains that you need the most information to. Yeah.
Thanks a lot, everyone. This was great.